Hi everyone, thank you so much for joining me. Sorry. Thank you so much for joining me. I'm honored to be here. I'm really excited to be presenting on double spin asymmetries at small x from exclusive vector particle production. And I'm an undergrad from the University of Washington. So there's some of my collaborators up here. This is a joint effort. We're hoping to release something in December, so please keep your eyes out for it. And I begin with just a brief overview of what I'm going to be talking about. We'll go over some motivation and some formalism, and then we'll digest the results in a leading-induced expansion, and I'll talk about some of the outlooks for it. So understanding the proton is central importance for all nuclear science, but our model is very incomplete. So we know the proton has spin 1/2, and we know it's a composite particle. And naively, you may think that, okay, there could be 3 quarks in it, and they might be choosing up, mostly down or something. But there was this pivotal experiment in the 80s that revealed that actually the total spin carried by these quarks is much less than 100%, and it could actually be nearly 0. And so where does the rest of the spin come from? Our conclusion is it must come from some from the quarks, some from gluons, the forces that mediate these quark interactions, and some from some kind of orbital dynamics within the proton. And so a fundamental question is then, how do each of these contributions add up to 1/2? So we were specifically interested in gluon contributions. Why gluons? Well, you can see here in this plot, the x-axis is inversely proportional to energy, the y-axis is proportional to the momentum fraction in the proton, and at low energies on the right side, you see, as you would expect, about 2/3 to 1/3 up and down quarks. But as we increase energy and move to the left, gluons become a very large role in the internal structure of protons. And so that means that they might be playing a very large and significant role in the spin structure of the proton. And so a large goal of nuclear science right now is to tomograph, or to create like a 3D image of the interior of the proton. And there's lots of different ways of imaging. The one we're interested in is called Generalized Parton Distributions, or GPDs, for these gluons, which contain information about their longitudinal momentum fraction and transverse position inside of the proton. So how are we going to actually measure these? We're going to be doing it at the upcoming Electron-Ion Collider at Brookhaven. This is going to be the world's most powerful microscope. So we're going to be able to image the interior of the proton through polarized electron-proton collisions. And so for the first time, we're able to polarize independently an electron and a proton beam simultaneously. And understanding the spin structure of the proton is a central goal of this project. So we're investigating how different polarizations of these beams could give us insights into these GPDs, or these images of the interior of the proton. The specific process we'll be studying is exclusive deep inelastic scattering. And that's when an electron and a proton collide, they scatter but remain intact, and then they produce this third particle, which is some kind of vector. The simplest case would be deeply virtual Compton scattering, or DVCS, which is where the produced vector is a photon, which is massless. But all of these processes are really nice because the cross-section neatly factorizes into an independent perturbative subprocess, and then these parton distributions, specifically the GPDs, that we'll be able to extract. And the observable we'll be studying at the EIC is spin asymmetry. So this is when you take a ratio of, you take the difference between different types of polarizations of the products of the reaction, and you divide it by the total cross-section. And historically, we've been able to do single spin and single beam asymmetries if you polarize just the electron or just the target. But these, in the economic limit we're studying, don't reveal any information about the GPDs, or specifically the real part of the GPDs that we're looking at. But double spin asymmetries, which are now possible at the EIC, are a kind of novel approach to this that would allow us to extract these GPDs cleanly. And here's a diagram below of like beams colliding, and then the vector meson measured, or the photon, and you compare these angular correlations to learn about the GPDs. So how do we actually go about doing this? I'm just going to go briefly through this without getting too lost in the math. As I said, the cross-section can be factorized neatly into a leptonic portion and a hadronic portion. So a lepton is just an electron emits a photon and scatters. That's completely independent of the proton. And then within the hadronic tensor, there's this wave function overlap, which is where information about the vector particle produced will be contained. And then that's scaled with this two-gluon exchange in a color singlet we call a pomeron. And that's where all the information about the location of these gluons inside of the proton can be extracted. So for the lepton, there's a bunch of computations we did, but the main result is just in this extension with polarization dependencies highlighted in red, you can see these are the components of that matrix that would contribute to these double spin asymmetries because they trend on the electron's polarization. And then for the hadron, my collaborators, Ben and Petru, were able to extract these three different decompositions of real scalar functions of the pomeron. One of them is P is spin independent, and then the PS and the PS perp are the spin dependent contributions to the pomeron. And then my work was to turn that into actual amplitudes, and we again got three different amplitudes here that depend on either helicity flip or helicity conserved protons. So all the indices here, the capital lambdas are the ingoing and outgoing proton polarizations, and then the lowercase lambdas are the internal photon and the produced vector particles polarization. And the way it's written in this green box is kind of like a matrix in a matrix. So you can see like the outer Kronecker deltas are like for the proton, and then these M's here are for they're only dependent on the helicities of the vectors. And so we don't need to go through all of these, but the main takeaways of these amplitudes are you can see these A's, which vary depending on the different polarization combinations, are where you would get all the information about your wave function overlaps. So this is the only thing that would change for DVCS or a massive vector meson. DVCS is really nice because we can have a fully analytic solution for all those A's, and so it's easy for us to come up with a neat formula. And then these P's are the pomeron, and the J's are bezel functions. So when we take the twist 2 expansion, which is if we imagine this quark pair that's going to combine into a photon or another vector particle, are very close together, it's a small dipole, we can digest these results, and this is where the GPDs come out. So pop that all, the audience, shout out, I've computed these for unpolarized cross sections, and we extended this to the polarized case, and we found these 4 GPDs that pop out from the pomeron structures we found. They are H, E, ET, and HT, which all are different combinations of either polarized or unpolarized gluon found inside a polarized or unpolarized proton. And so what we found when we did this for DVCS is implying these are all the real contributions for both longitudinally polarized electron and proton beam. You can see right away nicely we have E and HT GPDs pop out. But even more exciting was for longitudinal and transversely polarized proton, all 4 of these pop out, which is really satisfying, and now we can extract them in order to reconstruct the spin of the proton. So that's what we did next here. You can see, in order to actually get the total spin of the proton from these, we can just use a very simple dry-sum rule using these H and E after we locate them from these observables. And at the EIC, because of this new huge amount of kinematic range and these double polarization techniques, we'll be able to just pin these down, hopefully really nicely. And so as a summary of what I said, these GPDs right now are basically inaccessible. We don't know anything about them. They're very difficult to model. But these double spin asymmetries at the EIC will be able to unlock them much more easily as a sensitive probe. We found 4 of them from this technique. This was for DVCS, but if we wanted to do it for a massive case, it's very straightforward. We just change out those A's from the amplitudes. And then we're working right now on analyzing the feasibility of doing this at the EIC with some numerics. And then moving forward, once the EIC is online, either if we have current models of GPDs, we can plug them in and make some predictions, or given data from the EIC, we can fit and extract the GPDs from these observables. So that's all. Thank you so much. I'll take questions.
So we computed this in the small X framework, but are there existing calculation in the GPD framework?
What was that? Sorry.
Has this been computed in the purely GPD framework?
No. Right now, what we're working in is just with I think this was BF chaos, so we weren't taking into account saturation either, but we can also.
No, you're doing a small x approximation.
Yeah.
But is there large x computation in the GPD framework?
I believe so, but we haven't done it yet. No.
I don't know if it exists. Maybe this is new. So, if it exists, you can check the consistency.
That'd be a great check.
Yeah, you should.
Okay, thank you for that.
I actually have a question. I only recently, I've been kind of dabbling in some of the lattice QCD results and things like that, and I only recently have heard the word twist. What is twist? Like, I actually do have this, like, if you have a description of what twist is.
So twist is, you can see like these R's here for the keys is like the dipole size, and so the leading twist is just when the dipole is very small. When like the QQ-R pair here is like very close together.
Why is it called twist? Because I would kind of naturally assume that there's,
I've also wondered. I don't know if it has to do with like a phase or what.
yeah, I actually, like I said, I'm not, yeah, I've just recently come across this. Yes.
Can you explain what does X represent?
X is, well, I actually wrote X twice, but the small x that we're talking about is Yorkin X, which is a measure of like, for a given parton found inside the proton, what's its fraction of the total longitudinal momentum of the proton. Yeah.
I'm not experiencing this side of physics at all, but I think at some point in your presentation, you did mention that.
Can I ask a question? Ask yours to speak up so the room can hear the question.
Okay, sounds good. Is this audible?
Yeah.
Perfect. I'm not very experienced in this side of physics, but you did mention in the talk at some point that this can be used for a massive case as well, where now you're just looking in the proton. I was just curious, like, what do you mean by the massive? What do you mean by massive case? You mean?
So the massive case would be if instead of having DVCS where there's a photon produced in the result, we would have like J psi or something like that. That's like a massive particle, and for that, the thing that would change would be these hard factors for each of those would be like, for example, we need some other kind of model if we did like non-relativistic QCD, or we have something with like a lucid Gaussian, but it would be non-perturbable.